Okay, so we're going to talk briefly about deductive reasoning. And so deductive reasoning is the process of reasoning logically from given statements to a conclusion. Um, if you think of a detective, it's kind of like a detective. We're piecing together clues and making a statement at the end. So it's a more formal if this, then that, if this, then that reasoning, as opposed to before where we had inductive reasoning, was looking at patterns. So there's lots of examples. A doctor looks at symptoms to determine an illness. So if you have a sore throat and your temperature is above 100 degrees and your brother had the flu, then I conclude that you have the flu. Something like that, where we take pieces together and make logical conclusions between them. Like I mentioned before, a detective solves a case. They look for clues. Clues lead them to conclusions. A car mechanic has to diagnose your complaint and determine which piece is actually causing the problem and then fix it. So there's lots of ways that it works in the real world. We have what sound pretty scary, but we have laws that allow us to talk about this specifically. So we have the law of detachment. If a condition is true and its hypothesis is true, then its conclusion is true. Symbolically, what this means is if P then Q is a true statement and P is true, then Q is true. So if P happens, and if we know that if P happens then Q happens, then it must mean that Q happens. So if a gardener knows that if it rains, the garden will be watered. And then if we're given it's raining, what conclusion can he make? Well, he can conclude that the garden will be watered. It sounds obvious, but it's going to allow us to make statements. And sometimes it's hard to define what seem obvious or true in the everyday world. So if we look at these, we conclude some pieces. So if A is an acute angle, its measure is less than 90 degrees. And then we're given angle A is acute. And our conclusion is its measure is less than 90, because that's what our condition told us. And so we are using the law of detachment to be able to make a conclusion. Now we have to be a little bit careful. So we want to make sure that we have to be given the hypothesis. All right. So if we're given, you make a layup in basketball, you score 2 points, and then Jamie scored 2 points. We conclude that Jamie made a layup. Now, if we think about it, we weren't given the hypothesis. We were given the conclusion, right? We were given the 2 points. Now, can we conclude the hypothesis? In this case, we can't. If you're familiar with basketball, 2 points could come lots of different ways. It could come from foul shots, right? It could come from just a jump shot. So we got to be careful about using the law of detachment and making sure that we're given the hypothesis. We can always conclude the conclusion if we're given the hypothesis. It doesn't go the other way around necessarily. All right. We have another property called our law of syllogism, which states that if P then Q and Q then R are statements, then if P then R is also a true statement. This is very similar to properties that you looked at in algebra as we connect things. All right, so let's look at a couple of examples down here. So we're going to use the law of syllogism to draw a conclusion from the following true statements. If a quadrilateral is a square, then it contains 4 right angles. If a quadrilateral contains 4 right angles, then it is a rectangle. So if we look at our first part, there's a hypothesis, and then we see the 4 right angles is in both of these. That's what's going to connect them. That's in our property above. That's the Q piece that's going to connect the 2 statements. So 4 right angles, and our last piece is then it's a rectangle. So we can imagine taking the red, removing the green, that's our link between the two of them, and then adding the purple piece as our conclusion. So we're going to combine this into the red and purple. If a quadrilateral is a square, then it is a rectangle, which is also a true statement. All right, because a rectangle is just a quadrilateral with 4 right angles, so it's a specific case of a rectangle. So we can draw some conclusions. We're going to be given situations where it's all text-based, and we want to use either the law of detachment and or law of syllogism to draw a possible conclusion. So if the circus is in town, then there are tents at the fairground. If there are tents at the fairground, then Paul is working as a night watchman. All right, and then we're given the circus is in town. So what conclusions can we make? Well, we can make that from the first statement, the circus is in town, so there have to be tents at the fairground. And now that we know that there are tents at the fairground, we know that Paul is working as a night watchman. So our final conclusion is that Paul is going to be working as a night watchman. All right, so we're given that piece in red. All right, the purple connects our two, and so we can conclude finally the green piece, which is that Paul is working as a night watchman. All right. We have some very formal properties as we go through this as well. And so we want to remember what our postulates and axioms are. We assume them to be true. They're kind of starting points. We also accept these properties to be true. So these are deductive reasoning properties. These are going to help us with our proofs as we go through this. So we have properties of equality. So our equality piece here at the top. Properties of equality. And we have our addition property, which basically says if you start with an equal statement like A equals B, you can add the same value C to both sides and you still have an equal, you still preserve equality. We have the subtraction property of equality. Same thing as you start with A and B and then subtract C from both sides, you'll still have an equality. All right, we can multiply. If A equals B, then A times C equals B times C. We can also divide, assuming that C is not equal to 0. So if A equals B, then we can divide our two properties. This is called the reflexive property, which just says that A is equal to itself. We'll use that sometimes in our proofs. Sounds a little strange right now. But it allows us to basically make the statement that something is going to be equal to its own self. All right. We have the symmetric property. If A equals B, then B equals A. We can flip an equal sign around and preserve equality. We have the transitive property. This one is used a lot. It's very similar to what we just looked like, where we have some link, right? A equals B, B equals C, then A equals C. But in equality, we have that as our transitive property. So if Johnny is the same age as Sally and Sally is the same age as Susie, then John is the same age as Susie. We can take out that middle piece. And our last one is our substitution property. Often students confuse in a proof transitive versus substitution. Transitive has to look like this. Substitution just says if A equals B, then you can take out A anywhere and put in a B. All right? So we use substitution in solving equations all the time. All right. We can also have some more properties here, which is our distributive property. You should be familiar with this with our parentheses. And let's look at an example down here. So I want to solve this and justify my steps. So my first piece is I combine. I'm just going to look at it to begin with as how we'd solve it. And then we will look at our justification. So I know that 4 plus 2x plus 15 minus x has to equal 21. 21 is given as my entire line segment. And then I want to solve it. So I would get x plus 19 equals 21, or x equals 2. Now if I need to justify my steps, it's helpful to think about the y as going next to each line that I created there. So the first piece is our segment addition postulate, which tells me that if I take one piece of a segment and then another adjacent piece of a segment, it has to equal the whole segment. So it's my segment addition postulate. What did I do next to go from the first line to the second line is I just combine my like terms, right? So I have x's that I can combine. We could have really brought everything together with our commutative properties of addition and move stuff around, but for right now, we just want to start with this idea of proof, and so we just combine our like terms. And then my last piece, I got rid of that 19, and what allows me to do that is my subtraction property of equality. And so those are my y's. Those will start to get into something that we call, as you can see why, a two-column proof. I have my my statements and then I have my reasons as we go through this. All right. We also have properties of congruence, similar to the equality. Now remember, equality is for a quantity, congruence is for an actual physical shape. And so we'll be talking about segments and angles. So we have the reflexive property here. So if I have line segment AB is congruent to itself, AB. I have angle A is congruent to itself, just like before with our equality. I have a symmetric property of congruence. So if I have AB is congruent to CD, then CD is congruent to AB. I can switch those two around. And A congruent to B also means that B is congruent to A. All right. The last one is one we use a lot, is our transitive property. It links things. So I have if AB is congruent to CD and CD is congruent to EF, CD links the two, which means that AB is congruent to EF. Same thing with angles. B is linking the angles, which means that A is going to be congruent to C. So let's see if we can name these properties down here that allow us to justify these steps. So if x equals y and y plus 4 equals 3x, then x plus 4 equals 3x. So what happened here, let's try to figure it out, the y became an x. And what allows me to do that is my substitution property of equality. Right? I took out the y and I put in an x. Okay, let's look at the next one. So if I have x plus 4 equals 3x, then 4 equals 2x. Well, how did I get 2x? I took away an x from both sides, so that's going to have to be my subtraction property of equality. Okay. My last piece, I'm linking those two things with angle Q there, right? So P was congruent to Q, Q is congruent to R, and then R was congruent to S. So let's see what happens here. How did we come through it? I could figure out that P is congruent to R, right? And then if P is congruent to R, now I have a link between angle R up here and angle R down there, which is going to allow me to link it to S. So that is my transitive property from above, my transitive property of congruence. Right? We could think of it as substitution as well, as we were able to take out that piece. The reason why we look at it as substitution is here, right? I'm not linked directly with R and S. So it's not the R like I had Q and Q, right? I have R and S, and then I have P and S. So we want to think of that as a substitution. We can see our transitive property up here has the link between them.